You know what the strangest sentence in all of science is? Not the universe is 13.8 billion years old. Not there are more stars than grains of sand. Those are big numbers. Big numbers are easy to ignore. The strangest sentence is this one. An electron does not have a position. Not we don't know where the electron is. Not our instruments aren't good enough. The electron genuinely does not have a position. Until you look at it, and here's the part that should bother you. When we figured this out, really figured it out, some of the greatest physicists who ever lived went a little crazy. Einstein spent the last 30 years of his life trying to prove it was wrong. Schrödinger, the man whose equation describes this behavior, said, and I'm paraphrasing, "I'm sorry I ever got involved in this." So today we're going to figure out exactly what's going on. Not with jargon, not with math you can't follow. We're going to do it the way a curious person ought to, with experiments, with honesty, and with the willingness to be genuinely confused before we get to the good part, because the good part is extraordinary. Let me ask you something. When someone says the word electron, what do you picture? I'll tell you what most people picture: a tiny, tiny ball, maybe blue, maybe with a little minus sign on it, zooming around a nucleus like a planet around a sun. That picture right there, is wrong. It's not approximately wrong. It's not, well, it's a simplification. It's the kind of wrong that led to a century of confusion, because we kept trying to force reality into a shape it refuses to take. Let me show you why with a very simple experiment. One of the most important experiments in the history of physics, and all you need to understand it is a wall, a barrier, and a flashlight. This is called the double-slit experiment, and it was done first with light, back in 1801 by a man named Thomas Young, and then much later with electrons. And that's where things got very, very strange. Here's what you'd expect if particles were tiny balls. You fire a stream of electrons at a barrier. The barrier has two narrow slits. Most electrons hit the barrier and stop, but some go through slit A, and some go through slit B, and they land on the screen behind. What pattern do you expect on the screen? Two bands. One behind each slit. Simple. Obvious. That's what tiny balls would do. That is not what happens. What actually appears on the screen is stripes. Many alternating stripes. Light bands and dark bands spreading out across the screen. This is called an interference pattern. And it only happens with waves. Think of waves in water. Two waves meet. Where their peaks line up, the water goes higher. Where a peak meets a trough, they cancel. That cancellation is the dark stripe. That addition is the bright stripe. But wait, we weren't shooting waves. We were shooting particles. Now here's the part that gets you. Here's the part that got everyone. The physicists said, okay, fine. Maybe the electrons are somehow interfering with each other. Maybe they're bumping into each other mid-flight. Let's test that. So they slowed it down. They fired electrons one at a time. Single electrons. One electron. Wait. Another electron. Wait. One more. Each electron fired long after the previous one had already hit the screen. There's no way for them to interfere with each other. Right? They let this run for hours, recording where each electron landed, one dot, then another dot, then another, just scattered points, seemingly random. And then, after thousands and thousands of electrons had landed one by one, the interference pattern appeared again. Somehow, each electron traveling alone, with no other electron to interact with, knew to avoid certain spots on the screen. Somehow, it was aware of both slits, even though it's a particle going through one of them, unless it went through both. This is where the physics gets serious, and this is where a lot of science communication chickens out and says, well, it's just weird quantum stuff. But we're not going to do that. We're going to follow this thread all the way to the answer. Here is what quantum mechanics actually says. Before you observe a particle, before you measure it, detect it, interact with it in any way, it is not in a single location. It exists as something called a wave function. Now, what is a wave function? I want you to forget everything that word might conjure. It is a mathematical wave that represents at every point in space the probability of finding the particle there. Think of it this way. Imagine I'm going to flip a coin. Before the coin lands, where is the outcome? It's not heads, it's not tails. It's a kind of smeared out 50-50 possibility. The outcome doesn't exist yet. It will exist when the coin lands. The wave function is like that, except it spreads out through space, like a ripple. And a ripple can go through two slits at once. And the ripple from slit A and the ripple from slit B can interfere with each other, adding in some places, canceling in others, before the particle is ever detected. When the particle hits the screen, then the wave function collapses. The probability smear suddenly resolves into one definite dot, and the location of that dot was governed by the interference pattern of the wave. The particle is not somewhere specific. It exists as a probability until observed. Now, I know what question you want to ask. It's the same question Einstein asked. It's the same question Schrödinger asked. It's the question every reasonable person asks. And the answer, the real experimental answer is, the question has no answer. Don't take my word for it. The physicists didn't. They set up detectors right at the slits, little measuring devices designed to catch the electron to figure out definitively which slit it went through. Okay, but really, which slit did the electron go through? And they ran the experiment. And the interference pattern disappeared, just gone. The moment you try to know which slit the electron went through, the moment you establish that it is definitely in one location rather than a smear of possibilities, it stops being a wave, it becomes a particle. And two streams of particles hitting a screen make two bands. Not an interference pattern, two bands. The act of observing the electron, the act of gathering information about where it is, changes what it does. This is not a disturbance caused by clumsy equipment. Physicists have tested this with increasingly gentle measurements. The pattern disappears whenever the information about the path is available, not just when something physically nudges the electron. The universe seems to enforce this rule. You cannot know the path and see the interference. Pick one. This is what Niels Bohr called complementarity. Wave-like behavior and particle-like behavior are complementary. You can have one or the other, depending on what you choose to measure, never both. Einstein hated this. He thought it meant quantum mechanics was incomplete, that there must be some hidden definite reality underneath. He called it hidden variables. He was almost certainly wrong in 1964. A physicist named John Bell came up with something remarkable. He said, okay, Einstein thinks there's a hidden definite reality underneath quantum mechanics. Bohr says no, there isn't. Can we actually test this? And he showed mathematically that if Einstein was right and there were hidden variables giving particles definite properties before measurement, then certain experiments would have to obey specific statistical limits. And then the experiments were done, and those limits were violated. Over and over again in lab after lab, the universe produces statistics that are impossible under any theory where particles have definite hidden properties before you measure them. The universe is not hiding a definite answer beneath the uncertainty. The uncertainty is real. The probabilities are fundamental. Things do not have definite properties until those properties are measured. Not. We don't know the properties. The properties don't exist in a definite sense until the universe is forced by measurement to pick one. So, we come back to the original question. What is an electron? It's not a tiny ball. We've established that. Is it a wave? Well, it propagates like one. But when you detect it, you always find it at a single point. So it's not just a wave. The honest answer, the answer Feynman himself gave, is this. We don't really know what an electron is. We only know what it does. And what it does is this. It propagates through space as a wave of probabilities. When it interacts with something, that wave collapses and we find the electron at a specific location. The probabilities dictate where it's likely to appear. But until the interaction happens, there's no fact of the matter about where the electron is. I think I can safely say that nobody understands quantum mechanics. And he didn't mean that as a failure. He meant it as permission. Permission to stop demanding that quantum reality makes sense in terms of everyday objects. The math works, the predictions work, the technology built on this understanding, transistors, lasers, MRI machines, computer chips, solar panels, all of it works beautifully. We just shouldn't confuse the math works with I can picture it. Some things are true but not picturable, and that's okay.